Started.
You can see the board. Can you see the board? Oh, okay. All right. So let me now talk about how to define tensors in non-Cartesian coordinate systems. So we are. So again, let me go back to my example which I had yesterday. So we have a three-dimensional space. Let's choose this as my x-axis, y-axis, and z-axis. And any position, if I have a point, and this is fixed to an origin, so this is the position vector of that point. Components of this position vector are given as x, y, z along the x-axis, y-axis, and z-axis. Now let's assume now that I also have an infinitesimal displacement of this point to some other point q. So when I'm drawing it on the board, of course, it doesn't look infinitesimal at all. We mean that this dr is infinite. And I now choose. So let me again use our, as an example, cylindrical polar coordinates. So let's consider these as our non-Cartesian or curvilinear coordinates. So instead of having x, y, z, we have gone from x, y, z to rho, phi, and x. Okay. So now your r, we could write this as equal to. So that if you look at the position vector r, then in this component it's xi plus yj plus z in Cartesian. And if you look at dr, so if I look at this infinitesimal displacement, then you can see that in Cartesian coordinate systems, it's simply given by dxi plus dyj plus dz. And if I ask what is the magnitude of this displacement, so it's dr dot dr. And this is simply going to be dx square plus dy square. And what you can see here is that suppose I make the displacement, say, along the x-axis, keeping the y position and the z position fixed, then my ds is simply going to be dx. And similarly, if I do a displacement along y, keeping x and z fixed, then my ds will be simply dy. And if I make a displacement along the z-axis, keeping the positions along the x and the y-axis the same, then my displacement ds is simply going to be dz. On the other hand, now if I do the same thing in the cylindrical polar coordinates. So in cylindrical polar coordinates, I can write down my, so this is in Cartesian, okay? So this is a Cartesian description. This is also in Cartesian. But if I do in cylindrical polar coordinates, then you can see that I'm going to get del L by del R by rho, d rho, plus del R by del phi. So the infinitesimal displacement is simply going to be this. Okay. And yesterday what I did was I defined what these quantities are. So we defined our E rho as equal to del R by del rho. And I will define my E phi as equal to del R by del rho. And Ez is defined as scalar. And for that, the best way to do is just use the fact that in cylindrical polar coordinates, x will be equal to rho cos phi and y equal to rho sin phi. And z will be equal to z. So this gives you the transformation laws between the Cartesian coordinate system and the cylindrical. So we calculated these quantities yesterday. And also there what we saw was that while E rho and Ez are unit vectors, E phi is not a unit vector because we had this rho. So I can write this now as E rho times D rho plus E phi times D phi plus Ez times Ez. So this is what I was saying yesterday, that these quantities E rho, E phi, Ez are vectors which are lying in decreasing direction of rho, phi, and z respectively, which you can see directly from the relation for the displacement. And now you can see that also you can see from the definition which I gave you yesterday, you can see that E rho with E phi, the dot product is 0, and E rho with Ez equal to 0. And E phi with Ez is also 0. So these are mutually orthogonal to each other. So that's why you can choose E rho, E phi, Ez as a basis, because you have an orthogonal basis. And I can also tell you what to do. Okay, maybe you can just do it. Maybe I'll just write it down because it's better. So E rho is cos phi times I cap plus sin phi times J cap. E phi will be equal to minus rho times sin phi J cap plus rho times cos phi. So you can verify these relations. Right. So now if I look in the cylindrical polar coordinates, if I ask you what is dr ds, then ds is going to be simply d rho square. And what you will see from here now is that because E rho dot E rho, from here you can see that I can also write this here, that E rho dot E rho equal to 1, E phi with E phi equal to rho square, and Ez with Ez equal to. So I'm going to get here d rho square, then I'm going to get a rho square d phi whole square plus Ez. And so what this tells you now is that suppose I make now in cylindrical polar coordinates, I keep rho and z, say phi and z fixed, and I change rho infinitesimally by d rho, then my ds is going to be simply d rho. Similarly, if I keep d phi and say d rho fixed, so I only change it along the z direction, then my ds is going to be simply dz. But if I change infinitesimally along the d phi direction, keeping rho and z fixed, I'm still going to get. So if I put d rho equal to 0, dz equal to 0, then this implies your ds is equal to 4. Or in other words, rho is not simply, ds is not simply d phi. This is unlike what happens in your Cartesian coordinate system. It's getting multiplied by this factor rho, which is called the scaling factor. So yesterday I gave you more general version of this. So I told, that's where I stopped yesterday. So I said that if you take a general curvilinear coordinate system, and let's say that I call these coordinates as, so let's say now I have curvilinear coordinates, which I denote by U1, U1, U2, U3, right? Then I can write my R, or I can write my dr. So I have functions, then x will be some x of U1, U2, U3, or some function of U1, U2, U3. I could as well write it as x, but see, it's just like this, x equal to some function of this. So it's f1, and y will be similarly f2 of U1, U2, U3. So this is the transformation which will take you from xyz to the U1, U2, U3. So suppose I have this. So in this most general polar coordinates, or in this curvilinear coordinate system, then I can write my dx as equal to this. So my r, which was equal to x times I plus y times j plus z times k, can be written as equal to f1 of u. I'm just writing u here for this u1, u2, u3, I cap plus f2 of u j cap plus h3 of e. Okay. And then you can also see that I can now write my del r or dr as equal to. So now what I'll get is some, see, just like when we did this, so I can write my dr as equal to del r by, so let me write this like this, du1. So most generally I can write it like this, del r by del u2 into du2. So keep the cylindrical polar coordinates in mind, and then you can just calculate these quantities, and del r by del u3 into b. So explicitly, if I want to do the evaluation, I know these functions f1, f2, f3. It's like I know that x is rho cos phi sin phi. So then from there, now I take, for example, when I do del r by del u1. So take this and take the partial derivative of this right hand side with respect to u1. So u here represents u1, u2, u3. And once you get that, you will get exactly like we got here, e rho as cos phi I plus sin phi j. I will get this. Okay. And what I will now define is, so now what we will do is, I will define my E1 to be equal to del R by del U1. E2 should be equal to del R by del U2. And E3 is del R by del U3. So for cylindrical polar coordinates, U1 is rho, U2 is phi, and U3 is z. So I can therefore write this as equal to E1 times du1, or I can write it as du1 times e1 plus du2 times e2 plus du3 times e3. And of course, we want to describe you three-dimensional space should be such that your transformation should be such that my this E1, E2, E3, that means del R by del U1, del R by del U2, and del R by del U3, because these are three vectors, they should be orthogonal vectors, because otherwise I will not be able to describe a three-dimensional space. So my EI dot EJ should be equal to 0 if I not equal to J. But I can't say anything more whether the value is 1 or not, because in that, as we have already seen, for example, if this was E5, then E5 dot E5 was rho square. Okay. So now I can then write ds square as equal to root of, now if I look at the infinitesimal this thing, I will get this as E1 dot E1 times du1 square plus E2 dot E2 times du2 square plus E3 dot I write it not complex. So I get this. Now what we will do is, let me do this. That suppose I keep, okay, so let me call this E1 dot E1. So let's call this as equal to, define this as h square. See, now this must be, it's a real quantity. So I will define that whatever is this value. So I call this h1 square as E1 dot E1. Alright. Similarly, I will call h2 square as defining as E2 dot E2 and h3 square equal to E3 dot. For our cylindrical polar coordinates, h rho was 1, h5 was rho square, or h5 was rho, and h3 is 1. So if your u1, u2 equal to rho, u2 equal to phi, then you get back your cylindrical coordinate system. And in that case, your h1 will be equal to 1, h2 will be equal to rho, and h3 will be equal to 1. Okay. So h1, h2, h3, which are actually nothing but the length of these vectors. So I can write this now as root of this. h2 is equal to this, and h3 equal to this. These are. because your displacement is not simply going to be the displacement proportional to, it's not going to be simply the displacement along that particular coordinate du2, like for example du2 or du1, but it's getting multiplied by this h1 or h2 or h3. Okay. And before I go ahead, I'll also call this. So you can also see what will be the volume element. From the volume element now will be given as equal to h1, h2, h3, du1. So I would request you that work this out for two systems, but that is, this is the cylindrical polar coordinates. So this is cylindrical, and if you do it for these two, because these are familiar to you people, you will understand what's going on. And the other one which you do is for spherical polar coordinates. Because these are both curvilinear coordinate systems. So for the spherical polar coordinates, your u1 is equal to r, u2 equal to theta, and u3 equal to phi. And yesterday you already told me that for the cylindrical coordinate system, you get the, so if I have cylindrical polar coordinates for this system, you will get dv as equal to rho d phi, or let me write it like this, d rho d phi, and dz. So your h1 is 1, h2 is rho, and h3 is 1. And then you have d rho d phi. For spherical polar coordinates, what you have seen is that dv will be equal to dr, then you will get an r d theta, and you will get an r sin theta. So what you should be able to see is that h1 or hr will be 1, and h theta will be r, and h phi will be equal to r sin theta in this case. Okay, so verify this. Okay, verify that. For this case, hr equal to 1, and h theta is equal to r, and h phi is equal to r. Okay. So all that you need to do is use the relations, because we know, for example, for spherical polar coordinates, x will be equal to r sin theta, r sin theta cos phi, y will be equal to r sin theta sin phi, and z is equal to r cos. So use those functions, and from there you figure out what are the h1 h2. So what we find, so let me summarize. So what we have seen is that if I use a curve, so if I go to these curvilinear coordinate systems, like for example this u1, u2, u3, then I can still write my r in terms of those. In that basis, choosing the basis vectors then to be an orthogonal set of basis vectors which are given by EI, which is equal to del r by del u1. So these form an orthogonal basis. Orthogonal set of basis vectors. And notice the difference between this set and the ijk. Now your ijk, which is a Cartesian basis, is orthogonal, but it is the same at any position in space. On the other hand, if you look at EI, it will depend upon where you're located. So for example, we already saw that if I took cylindrical polar coordinates, if I look at E rho is cos phi I plus sin phi j. So obviously that vector will depend upon what is the value of phi. So that is the main difference, or the first difference from a Cartesian coordinate system to a non-Cartesian coordinate system. But nevertheless, I can choose such an orthogonal set. And then once I have this orthogonal set of basis vectors, then it means that any vector now, I can replace this as, I can write it like this. This is something I can do. Okay, but before I do this, I don't want to give this definition just now. We'll see something else. But notice one thing. You can ask the question now, is this the only thing which I have, or is the only basis, or do I have any other basis vector which I can use here? What you will find is that I actually have a choice of another basis set. So this EI's certainly form a basis set because they are an orthogonal basis set of vectors for our three-dimensional space. But if I define, now let's consider this quantity. So let me define for you now these quantities, epsilon I as equal to so again, to illustrate for you, for example, let's go back to cylindrical polar coordinates. So for cylindrical polar coordinates, u1 equal to rho, u2 equal to phi, and u3 equal to z. Okay. So this means you're taking the gradient of u1. So let's consider epsilon 1. And epsilon 1 by definition is the gradient of u1, which is nothing but the gradient of rho. So what this means is by definition, del by del x rho or del rho by del x times I cap plus it means del rho by del x times I cap plus del rho by del y j cap plus del rho by del z into k. That's what this definition means. Okay, by definition. Now, what is rho in terms of x, y? So we know that x is equal to rho cos phi, y equal to rho sin phi, and z equal to z. Now, from here you can see that what this tells me is that your rho is nothing but root of x squared plus y squared. Fine. And also, since I will require this, so you can also see that tan phi will be equal to y by x. So this is actually the inverse of this, and z will be equal to z. So if I want now del rho by del x, that you know the function x squared plus y squared. So it's very straightforward to do that. So you will get 1 by 2. So I'll just show you the first one. So it's x squared plus y squared. Then I'm going to get here a 2x I cap. And then from here I'm going to get a 1 by 2 times root of x squared plus y squared into 2y. So this is j cap. And since the rho doesn't have any z dependence, you don't get it. So it's going to be, so your epsilon 1 is again going to be a vector which will lie in the xy plane. But what is x? This is now x by x squared, root of x squared plus y squared. What is x by root of x squared plus y squared? Given that you have this cos phi and sin phi or tan phi is equal to y by x. So think about this. Again, you're in cylindrical polar coordinates. So I have like this. So I'm just drawing the xy plane. So this is your point, and this is rho, and this is phi. What will be x divided by root of x squared plus y squared? So this is your x and y. So let me also put this for example. Suppose I put this. So this is the angle phi. What is rho here? What will be this part, this much? Pardon? This is x, and this should be your y. Given that your point is having x, y, so if, and what is rho? Rho is root of x squared plus y squared. So what is x divided by root of x squared plus y squared? Elementary school geometry. Pardon?
Cos phi.
Yeah, this is nothing but cos phi. There you go. And what is this?
Sin phi.
Okay. So in this way you can evaluate. All right. So I can evaluate what is epsilon 1, and similarly you can do for the others. All right. So I've just given you an example of how we evaluate and what this actually means. And again, what you can convince yourself that okay, and all right. So in this case, let me just write it down here. So epsilon 1 you got it as equal to cos phi I cap plus sine phi j cap. Okay. Now similarly, let us do epsilon 2. Epsilon 2 by definition is del of phi. Okay, by definition from here. Because your u2 which is phi, so it's epsilon 2 is del phi. But you have here tan phi is y by x. So use that. See again, this is simply going to be del phi by del x. I'm not going to work this out, but you please work it out. Del phi by del y j cap plus del phi by del z k cap. Directly from here, because you can see from this relation there is no z dependence, I can see that this is not going to have any k. It will also, the epsilon 2 will also lie in the xy plane, so I'm simply going to get this. And del phi by del x, I mean you can use this. So take the derivative sec square phi d phi, or sorry, sec square phi del phi by del x from this y by x you have. Calculate it, and what you will find is that this will be equal to minus 1 by rho sine phi I cap plus 1 by rho times cos phi. And epsilon 3 we will find will be nothing but sec. Sorry, k. And what you can also see is that, so if I define now these three quantities, what you can see is that, okay, we also had E1, E2, E3, I've already defined for you those, and you go back and look at what this E1, E2, E3 was, you can see that, in fact, your epsilon 1 is nothing but your E1. And this is nothing but, you can think of it as 1 by rho square times your E2. And this turns out to be E3. You'll see, if you go back and see what you got for E1, E2, E3, you will find that these epsilon 1, epsilon 2, epsilon 3 will be related like this. And since you can see that epsilon 1, epsilon 2, epsilon 3 are actually proportional to E1, E2, E3. So in this particular case, so you can also check that epsilon I with epsilon j, if I take this dot product of these, it's going to be 0, I not, because I not equal to 2. So if I consider this set of three vectors, they are again an orthogonal set. And further, you can also see one more thing. That if I take now E1 dot epsilon 1, that's going to be 1. In this case, it is very trivial. But interestingly, you see now E2 dot epsilon 2, that is also going to be 1. See, because E2 had a rho factor, and then you have this epsilon 2, which is having this 1 by rho square factor. So you will see that these two together will become equal to. So you will get epsilon 2. This is going to be basically 1 by rho square times E2 times E2 dot E2, which is nothing but 1 by rho square times rho square, which is equal to. Okay. And also it's obvious that E2 dot epsilon 3 equal to 1. And further you can see that EI dot epsilon j equal to 0, I not equal to j. So the first, so interestingly, if I take E1 with epsilon 1, I get 1, E2 with epsilon 2 is 1, E3 with epsilon 3 1, and epsilon EI with epsilon j is 0. Or in other words, if I look at these quantities, what you can see is that from the, in fact, what you can go back is look at these definitions. What you can see is that I have this relation that EI dot epsilon j equal to delta. Here, please note, I am taking the dot product of PI's with epsilon j's, not with themselves. Okay, so when I have two vectors or a set of two vectors which satisfy this relation, what would you call this two set of vectors? Have you ever seen such a relation anywhere in any of your other courses? Okay, I will give you a hint. Think of some where you had when you had lattice vectors and then you define some other set of lattice vectors.
reciprocal space?
Yes, exactly. So you can say that this set of epsilon i's, so the epsilon i's essentially form a set of reciprocal vectors. This set. And in more fancy language, mathematical language, we say they are the dual vectors. But you don't need, I don't want to use those kind of very fancy language principles right now, but it's actually something which you are familiar with. And although I have illustrated this for the case of the cylindrical polar coordinates, but what you can do is now you can take these definitions directly and verify this condition for yourself. Because here I've taken the gradient of ui, and here this is the partial derivative of the r vector with respect to ui. So you can construct this scalar product and convince yourself that this is actually equal to, or this is verified, or this is true for any set of curvilinear, independent curvilinear coordinates. So when I write those curvilinear coordinates, these are independent curvilinear coordinates. I must have a set of 3 because out of 3 dimensions space, of course. Fine. Then in that case, even my orthogonal set EI, I can construct another orthogonal set epsilon j's, which are reciprocal to U's. So now you see what I have is therefore, and because this epsilon i's, but we also saw that epsilon i's are orthogonal. So that means I have 2 sets of basis vectors, EI's. So I have 2 sets of basis vectors, E1, E2, E3, and epsilon 1, epsilon 2, epsilon 3. Neither of these are necessarily orthonormal, but they are both orthogonal basis vectors. I mean, this is an orthogonal set, and this is again an orthogonal set. And further, what we can see is that this is reciprocal to this, and vice versa. I can call these as reciprocal to this. So now what it tells me is that I have a choice now to expand my vector. So a general vector we know I can expand because I'm having 3-dimensional space. Any vector can be expanded in terms of the basis vectors. So if I have some arbitrary vectors, okay, so let A be some vector. Then I can write my A to be equal to, okay, I could expand this in terms of, I'll write the coefficients in just a little while. Just for the minute, hold this, okay. So I could write, okay, I will call this as C1, C2, C3, just for the minute, afterwards I give the notation. Where C1, C2, C3 are the coefficients of this, or the components of this vector using the basis E1, E2, E3. Equivalently, I could have expanded it in terms of some other coefficients, epsilon 1 plus epsilon 2 plus epsilon. Where D1, D2, D3 are the coefficients now with respect to this basis, epsilon 1, epsilon 2, epsilon 3. It doesn't matter which I use, both are, because they are both representing either this expansion or this expansion, both of them represent the same vector. Now I'm going to introduce a new convention for you. Okay, now the standard convention is the following, that earlier whenever we expanded a vector, I used to write the basis vectors as some E1, and we used to write it as equal to say A1, E1 plus A2, E2 plus A3, E3. And since we only were dealing with one basis vectors, I just had A1, A2, A3, it didn't matter. But now since we will see that we will have reason to consider this basis and this basis, what we will do is we will develop some nice convention, and the convention is the following. The coefficients will be called like this. And in this case now, I will give a new notation. I will define now equal to. So this is nothing. It's just a kind of a new way of labeling things. Epsilon 1, E2 will be, so I'm So I'm going to define these 3 vectors, E1, E2, E3, but notice now the indices for them are on the upper, they have upper indices. Now I'm using both upper indices as well as lower indices, or both superscripts as well as subscripts. So I have superscript. So EI by definition equal to epsilon I, which is nothing but this, our usual case. Okay, so using this now, I will rewrite this expansion in the following way. And what we can see is therefore, what I have therefore defined is, so I have this basis set E1 or EI, E1, E2, E3, and the reciprocal basis set E1, E2, E3, for whom the indices I'm not going to use lower subscripts, but I'm going to use superscripts. Okay. So essentially for the reciprocal lattice, or not lattice, we don't have a lattice here, reciprocal vectors, I use a superscript index rather than a subscript index. And then what we are going to do is, I'm going to do this expansion. So when I do the expansion in terms of the basis vectors of E1, E2, E3, where you have used subscripts, now for the components, I'm going to use superscripts. And when I did the expansion in terms of the reciprocal vectors, for the components, I'm going to use subscripts rather than superscripts. Or in other words, now our summation convention becomes like this. That means, see, earlier whenever we had the summation convention, we used to have the same index must be repeated, and we only were worrying about subscripts because we did not have anything which was labeled by a superscript. But now I have objects, the same object which I can label by components which are having superscripts as well as subscripts. So you can see this, I'm writing it in this way, and this is the other way. So now your summation convention is like this, that repeated indices one as a lower index, or one as a superscript, and one as a subscript. And one subscript. Okay. So here I have one upper index on this side, and this is a lower index. So I can call it superscript, can also be called as an upper index, and this is a lower index. So it's a superscript, subscript. Here it is a subscript, superscript. Fine. So this is our new thing. And further now, what we will do is we will call this. So it's the same vector, notice, but I'm representing the expansion in either in terms of your E1, E2, E3, or this epsilon 1, epsilon 2, epsilon 3, or the reciprocal vectors, but you have these components. If I have like this AI with the upper subscript, these are called the contravariant components of this. Components of E. And if I'm using the basis of epsilons, or equivalently this E1, E2, E3 with the index on the upper side, then the AIs are called as the covariant components. So this is yet another way of, covariant comes. I've already given you one definition of covariant. That if I have an equation, I will say it's covariant, provided my left hand side and my right hand side transform in the same way. At least there we were discussing rotations. But this is another way covariance comes. So if your indices, so for a vector, we should have three components in our three-dimensional space. And if the indices appear on the top, then I will call those as contravariant components. Or in other words, if I'm making an expansion along this E1, E2, E3, then I will get the coefficients are called as contravariant. And if I'm making the expansion in terms of the epsilon 1, epsilon 2, epsilon 3, then those components I will call as covariant components. So these are, or then this is called a covariant basis vector set. Okay, it's because these are now covariant vectors, or this is called a covariant basis vector set, and this is called a contravariant basis vector. It's very interesting that if you have the index, because these indices are lower, so I will call this as a covariant basis set. So basically, if the index is lower or a subscript, then I will call it covariant. And if the index is upward, I will call it as a contravariant. That's by definition. And the main thing to notice now, your summation convention becomes that if I have two repeated indices, always it should happen that one should be upward and one should be lower. So for example, now let's go back again and see our. Let's see how what this means, for example. So let's see what was our dr. Dr, what was dr by definition? Dr was del r by del u1. Yeah, so I had it as del r by del u1. I just want to show you what are the covariants for something which you have. So this is a vector, you know, dr. This is a displacement vector, and by definition, this was du1 plus del r by del u2 du2. Just now I'm just using the familiar definition, but we'll see that now I have to change this definition. Del r by del u3 into du3. This is how I called it earlier. But now you can see this is nothing but e1, e2, e3. So I'm going to write this as, so now in this new convention, this is going to become e1 times, and write this as du1 times e1, okay, plus du2 times e2 plus du3 times, or in other words, what we were calling earlier as u1, u2, u3, now I will call that u1 equal to rho. Again, I'm going back to our cylindrical coordinate system just for the sake of convention. This is in the set, which is where I've expanded in terms of e1, e2. Now the same vector d, this should be equal to du1 e1 plus du2 e2 plus du3. See, this we got simply from our definition of R. But now this, when I look at the second line of this, here I'm now making an expansion in terms of the gradients of U1, of the U1, U2, U3. Because E1 is nothing but del of U1. Okay. Similarly, E2 is nothing, this one, the contravariant E2 is nothing but epsilon 2, which was gradient of your phi. And the contravariant E3 is nothing but the gradient of Z. Now the coefficients are this. Okay, verify for yourself now. Okay, I'll ask you the question now. Are du1 and du1 or dui and dui the same? How do you get the same answer? What do you think? Okay, if you go back to again our example, what was E1? E1 was nothing but E rho. So for the cylindrical thing, it was cos phi times I cap plus sin phi times J cap. And if you look at your epsilon 1, I gave you the definition. Epsilon 1 is the same as E1, was also the same. So E2, which is equal to epsilon 1, is going to be the same. No problem. Same thing you will find for E3. But look at, sorry, this E1. On the other hand, if you look at the covariant E2, then this was by definition minus rho times sine phi I cap plus cos phi times j cap. On the other hand, the contravariant E2, which is equal to epsilon 2, will be equal to 1 by rho square. What did I get? 1 by rho square sine phi. I just started writing it down. So what was it?
Ma'am, it was minus 1 upon rho sine phi I
plus 1 by rho square cos phi. And what you can see now is that your contravariant E2 is not the same as your covariant E2. Because you see the covariant E2 is minus rho times sine phi I cap plus cos phi j cap, while the contravariant E2 is minus 1 by rho square sine phi. So there's extra factor of, here if you have a rho factor here, I have here a minus, or actually I have a 1 by rho square. Minus signs are the same. This is also rho square. Okay. So automatically this will tell you therefore that, for example, in this particular case for the cylindrical polar coordinates, it will turn out that the covariant du1 and the contravariant du1 are the same. Similarly, you will find that the covariant du3 and the contravariant du3 are the same. But what you will be able to check for yourself is, which you can see directly from here, that the covariant du2 and the contravariant du2 are not the same, because the covariant E2 and contravariant E2 are not the same. So the scale factor will come. They will be factors of this rho coming into this. So what we want now is to develop a language, okay, and become important. See, okay, where? So as on the other hand, if you look, okay, just before I go ahead, if I looked at Cartesian coordinate systems, then you can see that whether I have covariant or contravariant basis, it will be the same. In that case, if I had x, I, j, k, so you can see that by definition, del r by del x will give me again I. So my E1, E2, E3 will be I, J, K, and the covariant E1, E2, E3. The contravariant one will also be the same, I, J, K. So there is no difference in the Cartesian coordinate system. There is no difference between the covariant and the contravariant basis sets. So in fact, we can just forget about contravariant. We can just keep to one set. But already here you can see that when I went to cylindrical polar coordinates, my covariant and contravariant basis vectors are different. And therefore, if I look at the components of a vector, in this, either if I use a covariant basis or if I use a contravariant basis, I'm going to get two different answers for the components. So now you can ask the question, when do these such non-Cartesian systems or curvilinear coordinate systems, the description of these become important? Why do I need to go into these kind of curvilinear coordinate systems? One is, of course, even in our usual kind of physics, for example, in quantum mechanics, what you've seen is that when I want to solve the hydrogen atom problem, then you found that because of your symmetry, the spherical symmetry there, it was more convenient for us to use a spherical polar coordinate system rather than a Cartesian system, because it made the calculations much easier. So one is that symmetry considerations often force you to use curvilinear coordinate systems. In electrodynamics, for example, if I want to talk about the potential due to a charged ring, or say a current current flowing through a ring, then you have automatically a cylindrical geometry. So then again, you will find that it's more convenient for us to use cylindrical polar coordinates. So again, in that case, it will be convenient for us then to build up a description of various physical objects in terms of transformations or in terms of this curvilinear. So that is one. But more importantly, and really this is where the whole beauty of this tensor analysis comes, is that you are forced into this curvilinear coordinate systems. For example, when you talk of general relativity. So if I want to talk of gravity, if I want to take gravity into account and or relativistic effects into account, then what you will find is that I really need to use, or most generally I will find that once I take gravity into account, then my system or my coordinate systems are really not flat space. but you need to use some kind of curvature. You need to take curvature into account, and then they kind of more general such curvilinear coordinate systems become very natural to use. And in fact, all of this beautiful tensor analysis is most important in relativistic theories, whether it's classical gravity or whether it's relativistic quantum field theories. So there you would really find that extensive use of such tensor analysis, and also this whole idea of covariant and contravariant vectors and so on. So that's why we are going into this language of, and we will see that this, more about this a little bit. Now we also saw that. So basically, what we are now looking at is how to define. So I'm given a coordinate system. I'm using curvilinear coordinates now to describe my coordinate system, and then I'm looking at how a displacement vector can be described in that curvilinear coordinate system. And what we have seen is that I can use two different orthogonal bases. One is either the covariant basis set, or I can use a contravariant basis set. And if I use this covariant basis set, then the components are called as the contravariant components for the vector. If I use the contravariant basis set, then the components are called as the covariant components. And why we have this opposite kind of identification is because our repeated summation now demands that the indices always you do our one upper, one lower. Now let's go back to asking what is the magnitude of the displacement. So already I showed you that dr can be now, because it's after all a vector, can be expanded either like this or either like this. And if I look at this now, suppose I've taken I've made the expansion in terms of this basis, the covariant basis, then I can write this as du1. So now I'm using so this is this, dr I've used expanded in terms of this basis, the covariant basis. Then I'm taking the scalar product of this with, okay, so I've used the repeated summation now. You can see that I and I are repeated. So this means du1 e1 plus du2 e2 plus du3 e3. And that is going to be dotted with this. For dr again I've used this. And again I've used repeated summation or some repeated index summation. So j is there. And you can see here I've used I must use another dummy index. So I use j. Again this means du1 e1 plus du2 e2 plus du3 e3. One is upper, one is lower. And this I can write now as dui duj, because these are just numbers or functions. And I have ei dot. Now, most generally, what I can do is now, and we've seen that ei dot ej, at least for our cylindrical polar coordinates and so on, it is 0 if I not equal to j, but in general, for I equal to 1, it's not 0. Sorry, it's not even equal to 1. So what I'm going to do now is define for you now a quantity like this. So let me define. So I'm going to define now these coefficients, because finally ei dot ej will be simply a number, because after all it's a dot product of two vectors. So let me define now this quantity gij to be this. Okay. So you're going to get a set of 3 or 9 numbers, because when I takes value 1, 2, 3, j also takes values 1, 2, 3. I'm going to get a set of 9 numbers. And I'm going to write this as called as gij d1. So defining that this set of 9 numbers, I can write my ds square to be like this. Okay. And what you can see is that for your cylindrical polar coordinates, for example. So let me arrange those. Obviously, this is 9 numbers, and you can see it's like a matrix form. Gij will be of this type. If I look at the matrix, this will become 1, 0, 0, 0, H2 square, because this was my EI dot EJ, I called it as H2 square. And 0, 0. And this is nothing but because E2 dot E2 for our cylindrical polar coordinate system came across. Okay. And more generally now, because we have chosen an orthogonal basis, my Gij will be equal to 0 if I not equal to j. This is for our orthogonal basis which I have chosen, okay, for this particular case, because my EI dot EJ was 0. And it's equal to HI squared. Gi equal to this. No summation over that. So if for spherical polar coordinates, what you will get is you will get 1 here, then I'm going to get an R square here, and I'll get an R square sine square. So from here, what you can see is that, so if I look at this matrix now, think of it now as now just a matrix. So what you can see is now determinant of G, Ij, that matrix. So most generally it's going to be this. So in general, therefore, I can write my G to be like this. I will simply write this as most generally that H1 square, H2 square, which were our scale factors. Okay. And what you can see is that determinant of G then will be nothing but H1 square, H2 square. And so therefore what you can see is now if I use this definition, then my magnitude of an infinitesimal displacement then ds. So ds squared is becoming Gij dui duj. Okay, where I have defined this G to be like this. And if you go back and look at the volume element now, dV, then what you will find was that was nothing but H1 square, H2 square, H3 square. Okay, I'm using now du1, du2 to du3 because we are using contravariant components for our user efficiency. And this whole thing, H1 square, H2 square, H3 square, I can simply write it as root of determinant. Sorry, it was H1, H2, H3. Let me write this. If you remember, it was H1, H2, H3. This, I can write it as equal to root of determinant of G. So the volume element simply becomes most generally in this fashion. Okay, again, I've used an orthogonal basis here, so which is why I don't have off-diagonal elements for my G. All right, I simply got this. But okay, we'll see a little bit more about this. So once I introduce this object, so I've got this now this Gij, which has 9 components, right? So 3 by 3 matrix in our case. And we see that I can write my infinitesimal displacement magnitude in terms of the G's. I can write the volume element in terms of the determinant of G. And here I defined Gij in terms of the scalar product between the covariant vectors Ei and Ej. Now we could also equivalently define Gij to be Ei dot Ej. There is a scalar product of this, of the contravariant vectors Ei and Ej. And Gij, if you look at the matrix, is the inverse of G. So the with the 2 indices on top is the inverse of. So when I write this square bracket and Gij here, it means like I'm thinking of the matrix. So you will find that this matrix is the inverse of this matrix. Now you see some more things. I'll say a little bit more of G just in a while, but you can see the advantage of this G in the following. Now let's consider the scalar product of two arbitrary vectors. Okay, so let A and B be two vectors. Be any two vectors. Okay. Now, if I take the scalar product of this A as an vector, so I can expand this in this. Let's say I expand it in this using the covariant basis Pi, and then I take the scalar product with again where I've expanded with this. So this I will get then as AI, sorry, Bj times, because I've taken now Ei dot Ej, but this is nothing but my Gi. So the scalar product A dot B can be written as AI Bj. So I'm taking the contravariant components for the A's and B's, and I have this G with the Ij in the load. Fine. But I could have also done this as, okay, I'll do a little bit more and then tell you what is this G in just a little while. See, I could have also expanded this in the covariant or in the contravariant basis set, in which I'm going to get EI dot BI, BG, EG. So I'm using now the contravariant basis set. So then I'm going to get this as equal to AI BG. Because EI dot EG are defined like this, I'm going to get a G. And both these are equal. Okay. And further, one more I will do. This is sort of curiosities. One more thing I can do. I can also define now, let me define Gij as equal to EI dot EG. So you can see now I have this object with one upper index, one lower index, and just taken the dot product of the contravariant E with the covariant E. Right? Okay, so this I can also write it like this: EI dot, because now what I've done is the A vector I expanded in the contravariant basis, and for the B vector I expand now in the covariant basis. Fine. And this is going to give me then AI Bj, and then I have got EI dot Ej. But what is EI dot Ej? See, what is the contravariant EI? What were our contravariant EIs and the covariant EIs? What was the relation between them? The covariant EIs was the definition of E1, E2, E3, which was del R by del U1, del R by del U2, and del R by del U3. What was the contravariant E1, E2, E3? They were the epsilons. So how are epsilons and these E's related? So if you remember, these were reciprocal vectors. So this is going to be 0 unless. So what we will get therefore is that this is nothing but AI BI. So now you can see that I have the scalar product where you have with the repeated index summation, one contravariant, one covariant, and verify for yourself. Now I could also have done it like this. All right. So I have introduced this object Gij, which is a set of 9 elements. And you can see now the volume element is given in terms of root of determinant GU1, and the displacement or ds square is that means the distance square is given in terms of Gij, dui, dj. That means I can make displacement is like the magnitude of the thing is given in terms of that Gij, dui, dj. So that's why this Gij is called. It's actually okay. We have not shown this, but we will show that this is a tensor. It's a second rank tensor. And this particular tensor is called a metric tensor. Metric tensor metric means it's measuring. And here from this definition, basically it measures the distance. So, and here you can see that it's also gives you an idea about the volume. Okay, so I'll continue with this. I forgot to tell you. This is going on.
Just phone somebody.
So I just want to tell you that tomorrow I'll take one extra class at 11:15. Is that fine?
No.
I
You
don't
should
know.
reply. Maybe the power generation.
I'm not getting any reply. I don't know whether.
It's Gariba.
So 11:15. 11:15. Okay. Because I would like to complete this tensors by tomorrow. So see you tomorrow. So I have to stop this.
Hey, go to that MST.
Where is MST?
इसको बोलो इसको.
हाँ?
ये
ये है क्या?
That's
हाँ.
it.
इसको प्रेस करो. या प्रेस करो.
हाँ. Okay.
Stop recording. And then leave the meeting. This is
In
end meeting first. Okay. End.